Okay, so the big thing that we went over yesterday was parameterizing surfaces and how to parameterize surfaces. So let's just scroll up here real quick. We talked a little bit about circulation density and divergence. Again, these aren't really like huge concepts, but these are definitely worth kind of knowing the ideas. Divergence is um, it keeps track of how much sort of everything's pushing away from you or pushing towards you. That's a particle. And circulation density is kind of how everything or how particles, rotate as they move around. So positive positive divergence means pushing away. Negative divergence means pushing towards. Circulation density, positive circulation density means a counterclockwise rotation. A negative circulation density means a clockwise circulation of the particles, not necessarily the entire, vector field. Um, yeah. And then we got into parameterizations of surfaces and surface area. So parameterizing surfaces, again, the idea, and we're going to go over it a little bit more today. The idea is you always want to start off with some r of blank blank is equal to xyz, and then use whatever you're given about the problem to help you narrow it down to two variables and um, narrow it down even from there, right? We saw that xy wasn't really a good choice here because of this kind of square root of x squared plus y squared. And if we were looking at the shadow of this cone, we would have a circle rather than a square. And so it turned out that r and theta were much more useful in this problem. We looked at partial derivatives. There's partial derivatives now. We're going to use them for these cross products to not necessarily check that a surface is smooth, but to compute surface area and surface integrals. Right, so we looked at surface integrals or surface area here, and we mentioned that kind of the Jacobian for going from d sigma to duv, whatever your surface is parameterized in, we need to add in this magnitude of the cross product of the partial derivatives of r. And I included this warning. It's not clear why this warning, we really need it, but we'll see it in one of our examples today. So the idea is, if you're using r and theta, putting an r in here is no good. Chances are it won't just be an r. You really do need to compute this magnitude of the cross product. Okay, so questions on anything we did yesterday? Doesn't look like it. Okay, so let's continue on. So we just ended with this example here, parameterizing this cylinder that's kind of shifted off a little bit from the z-axis. I'm trying to figure out. Let's just go through. We gotta. Well, no, we'll do another example because I don't know how the cross product of the derivatives will work out here. I think it'll be fine. Because we have thetas only in these two components and then z in this component, and so there's going to be a good amount of zeros here. But maybe we'll skip on this and do another example, just so we can see the whole process out, kind of one day. So let's find the surface area of the surface cut from the bottom of the paraboloid given by x squared plus y squared minus z is equal to 0. By the plane z equals 4. Right, so the idea is, again, a paraboloid is kind of in this case, it's an upward facing bowl that goes off for infinity. Think of it as, kind of a parabola in the x and y directions. And so what this says is, well, we're cutting it at the plane z equals 4, and we're taking the bottom part of it. All right, we'll try to draw a picture here. Won't take too much time on this, but okay, so this isn't going to work out great, but it'll be fine. So we kind of have this y or z and y parabola. And then we would have the same thing in the x and or the x direction. I don't know, this is going to be fully accurate, but maybe something like that. And then the cross sections are some sort of circle here. Have that paraboloid going back that way. So something like this. I don't know. But again, just think of the bottom or, a bowl, basically. So the first thing we need to do is parameterize the surface. So this is what we're calling S here. So again, we want to start out with R of blank blank is equal to a vector XYZ and try to use this equation, because that's kind of all we're given here, to help us out. Well, here we can see that we can easily solve for z. Z is equal to x squared plus y squared from this equation. So that's a good first step. And we might notice again that, like in this problem, if we were to use the variables x and y, we would get kind of a circle shadow. It's not quite what we want. We want some sort of rectangular bounds here. So again, we should probably change this over to polar coordinates in this case. And this works out pretty well. Something like this. Right, so the last thing for the parameterization is that we need bounds for r and theta. Theta isn't too bad, 0 to 2 pi. For r, we want to go from 0 because that's the middle sort of point here. In the outside point, well, again, if we were to kind of cast a shadow down, we would see a circle of radius 2. So that's one way to get this upper bound for r. The other way is, well, if z is equal to 4, but z is also equal to r squared, then you can say r squared is equal to 4, and then so the upper bound for r should be 2. So that can be another way you can go through and search for radius. Right, a lot of these ways you can do algebraically or you can do geometrically. Okay, so we have another example where we have r and theta as our two variables for this surface. And now what we need to do is find the surface area. So let's just write it down again. The surface area is a double integral over the region, and this is again in terms of u and v. Just write that down there just to remind ourselves. Surface area, volume, area, all that stuff, we're integrating the function 1. And then we have the cross product of the two partial derivatives, or the magnitude of that. I'm going to write dA, but this should be a dr d theta. So I guess I can erase this u and v and think of this as r and theta bounds. And since this is a rectangle in terms of r and theta, it doesn't really matter which way. I mean, it might matter depending on kind of this, but as far as the bounds go, it doesn't really matter. Okay, so I'll pause here. I'll say our next goal is to find the magnitude of this cross product, but does this whole parameterization thing make sense? It's also the problem with online teaching. You know, in class, I could just look around, kind of gauge your guys' faces. But now, you know, I can't really see if anything is actually setting in, which is really unfortunate. So I'm going to assume this all made sense, or mostly made sense, and keep going. So we need to look at the partial derivatives, r and r theta. Where's our parameterization? There it is. Great, so take the derivative with respect to r for all of these. The first two, the r's go away, you just have cosine of theta, sine of theta. Third term, you get a 2r. And for the derivative with respect to theta, well, cosine turns into a negative sine. Sine turns into a cosine. And r squared doesn't have any theta, so we just get a 0 there. All right, and now the cross product. So again, it doesn't really matter which order you take the cross product in this case, because we are taking the magnitude of this vector. So that's pretty nice. So let's check this out. So again, for the first component, we take 2 times 3 minus 3 times 2. So we should have a sine times 0 minus a 2r squared cosine. For the second term, we have a negative out in front of everything, and then a 1 times 3 minus a 3 times 1. So we get a cosine times 0 minus a negative 2r squared sine of theta. And then for the last term, we get a 1 times 2 minus a 2 times 1. Our cosine squared minus a negative, so we'll just do a plus there. R sine squared. Again, we've done cross products throughout the semester. You know, if you don't quite remember it, this is kind of your it's kind of a sign to say, hey, we need to remember these things. We need to get used to taking cross products and be relatively quick at them. So again, whatever form that you care to do a cross product in, you need to do it somewhat efficiently. Okay, so let's write all this out again. We have a negative 2r squared cosine of theta. Second component, we have a bunch of negatives running around, but overall we get a negative 2r squared sine of theta. Third component, we have a sine squared plus cosine squared. We can factor out the r to get that, and so we should just have an r. Now for the magnitude of this vector, this is equal to the square root of each of the components squared, or the sum of those. So we should have a 4r to the 4th cosine squared of theta plus a 4r to the 4th sine squared of theta plus an r squared. Now again, we can do the thing where we factor out and we have the sine squared plus cosine squared. So we get 4r to the 4th plus r squared. We do a bit more factoring here if we wanted to. We could factor out to get something like r times the square root of r squared plus 1. You could factor out a 4 out of all these things, but you know, keeping as few fractions as possible is kind of nice. So this is one form of it. You don't have to factor out this extra r. You can just leave it as the previous form. That's fine. I'm not going to deduct points or anything like that. Yeah, so this is fine. Okay, so
Andy,
once we have, oh yeah, go ahead.
I've got a question about just calculating r sub r and r sub theta.
Yeah.
How do you do that?
Right, so these are just the partial derivatives, right? So this r sub r, right? This is, you could just think of as del r del r. But this is the thing where you take the partial derivative of each of these components with respect to r, right? So
Oh, gotcha. Okay, that makes sense. Thank you.
yep. Right, so it looks something like that in each of the components. Yeah. Great, good clarifying questions. Yeah. Okay, so scroll back down. All right, so one thing to notice is that this in the box here, this is not r. Right, so we mentioned before, the big warning before is that you can't just substitute in, if you have the variables r and theta, you can't just substitute in r d theta. In this example, we have to substitute in r square root of 4r squared plus 1 dr d theta. So when we're looking at our integral, surface area is equal to the integral from 0 to 2 pi, because those were our theta bounds. 0 to 2, I think. Yeah, 0 to 2 for our r bounds. And then we're integrating the function 1, r square root of 4r squared plus 1 dr d theta. Right, so again, this kind of exemplifies the warning. You can't just plug in an r here. You have to go through this process. And this integral is actually possible to do. Right, it might not look like it, but you can do a u substitution for this r. You could say u is like, well, I mean, you could actually just say u is everything in here, and then du is in terms of r. So you can actually get away with that, which is nice. And if you go through it all, it's a bit of a mess. But apparently, you get something like pi over 6 times the quantity 17 root 17 minus 1. So again, it's a bit of an integral to do, and maybe I recommend doing it, or at least trying this out once, just to remember how to do all these sorts of integrals and stuff like that. But we're not going to do this in class. So the other thing I want to mention is that these problems, like you may have noticed, they take a little while. And so if we go through more of these problems, I will probably skip some of the steps, depending on how many problems per class we do, right? Because this parameterization stuff is kind of new. It's similar to parameterizations that we did a little bit before. These partial derivatives, right? We've taken a ton of partial derivatives before of all sorts of functions, so it's just kind of applying this to another vector. Cross products, we've done this before. Magnitudes of vectors, we've done all that. And so it's just, again, a lot of these new applications is, well, they're really just new applications, right? We've done most of everything, each part of it, but putting it together in a different fashion, that's kind of a new thing here. And so the point is, this stuff takes a long time, kind of like my rambling. And so I will try to not go through all of it. And actually, that's the last example that I have for this section. Again, I recommend doing a lot more examples, a lot more problems, because this is can be a bit tricky, but they do take a while, unfortunately. So if there aren't any more questions, we'll be moving on to section 16.6. Oh, actually, while we have a pause, this reminds me, I don't know if this got posted in, I think it got posted in the discussion board a while ago. And I see the discussion board is pretty active. So for problem 1 on homework 10, I want to clarify something. So it says, give an example of a conservative vector field and of a vector field which is not conservative. So the idea of this problem is not to give me real world examples of each of these things. But the idea is to write down 2 vector valued functions and give some sort of reasoning that one of them is conservative and one of them is not conservative. So an appropriate answer would be maybe some function that you write down, blah, and the gradient of that function as your vector field. And then something else where it very clearly fails part of the component test. You don't have to necessarily show that, like, oops, that like this is not true. But if you give me a vector where it's very obvious that I look at this and I'm like, okay, well, those are definitely, one is 0 and one is 1 or something like that. That will be fine. But I do want these out in their component form like this. You don't need to give a ton of sentences reasoning why. You don't need to, go above and beyond for these things, but you do need to write these vectors down and make it somewhat obvious based on everything that we've gone through, right? And so, yeah, I'll say that. If you write something down, you're like, well, I don't know if that's clear. Maybe try a little bit more explanation. But again, I'm not looking for a ton here, but I am looking for something. Okay, moving on. Section 16.6, surface integrals. And the great thing is we've already done a lot of this section. Like a lot of it is built into section 16.5. Some of the annoying parts are parameterizing surfaces. So you'd have to do that for each of these problems unless it's given to you. We've talked about this extra sort of Jacobian term that shows up. And so otherwise it's just kind of substituting in functions. So let's go through and properly define this. If a surface S is parameterized by R of uv, which is a vector vector valued function in two variables, with uv in some region. So R is your region on uv, or defined on uv. And G of xyz is a continuous function on S, so on our surface. Then the surface integral of G over S is the following. I'll write it out on the next page. So again, it's a double integral of kind of G of x, y, z. Writing variables here might not be the best thing, but oh well. So in its kind of abstract notion, this is what you would write down. If we were looking to compute this, again, we want this in terms of UV, whatever we have our surface parameterized by. So we have the region R. Move this over a little bit. We have G of substituting everything in. So X of U comma V, Y of U comma V, Z of UV. For D sigma, again, we need to substitute in the cross product of the partial derivatives, the magnitude of that. And then we'll just write out du dv, just to be extra explicit. This is an integral in terms of those two variables. So again, the only thing that changed from surface area to now is we potentially have a function g in here that we need to worry about. Otherwise, it's the exact same thing. We need to parameterize our surface. We need to find this magnitude of the cross product of the partial derivatives. And forgive me, that should be a v. But yeah, everything else is pretty much the same. So let's do an example. Just a quick one. Integrate, or at least set up the integral g is equal to x squared over the paraboloid. From earlier. Right, so again, we can kind of scroll up. Just to recall what that paraboloid bounds were. 0 to 2 pi, 0 to 2, 4 square root of r, square root of 4r squared plus 1. Right, so this is everything that's copied down from above, but then we need to plug in this x squared for our function, but we want x squared in terms of our parameterization. So since we're using polar coordinates, we should have an r squared cosine squared. So overall, this is our integral. I don't have the calculation for it, but Wolfram Alpha, you could go through and do that. And I don't know if you can actually, I think you need a bit more, I think you need to be a little bit clever about this if you actually do want to go through and solve it. Right, the reason I say it, well, maybe not. Yeah, maybe not. Maybe you don't have to be super clever about it, but it is a little annoying, right? You can choose this whole thing to be u. Again, you would get an 8r for your substitution, so you'd have a bit of you'd have a constant out in front, but then you'd have an r cubed out in front, so like you'd have a u cubed times square root of u. You can rewrite this as a u to the 7/2 or something like that. You might need to worry about continuity and stuff like that and worry about negative numbers, but I don't think you really do because of these bounds. So it all should be doable. Again, this is a bit of a mess, so we're definitely not going over this, but apparently I didn't do it any other time. So either I found out it wasn't possible or I said, wow, this is going to be a pain. And so we're not going to go through it. But either way, this is the setup. This is the idea for a more general integral. Let's do another example. So this is just kind of a note, actually, first, that we will use in the next example, given multiple surfaces. You can integrate over each and add them up, right? Just like anything else where, if we have a curve that's broken into multiple parts, we just integrate over each of the parts. So for example, if we have something like a cube, something like this, this normally, well, if this is a rectangular prism, then you can't quite cut it down as much, but regardless, you would need to break this into 6 different surface integrals. But if this is a nice cube, then you can just multiply by a 6 at the very end of the day. So we will say that this is a unit cube. So we could think about this being sort of set in the XY plane. It's not quite drawn perfectly, or sorry, the 3D, and again, it's not quite drawn perfectly, but you can think of this as X, Y, Z. This back left corner is sitting at the origin, and each of these lengths is 1. So this is kind of how we think of the unit cube here. Then for this example, we will set up the integral, but integrate the function x, y, z over So this is a bit tricky. Sorry, I don't think we will. We'll just stick to my notes. So what I wanted to do was integrate this function over the entire surface of the cube. But that's going to be a bit unwieldy. That would actually, like, you would honestly need 6 separate surface integrals for. It may turn out to be that, like, you know, it's probably okay if you use some symmetry here, but like before doing all of the work, I don't know. So maybe I'll get into maybe I'll say something more precise than that in a little bit, but let's just integrate this function over the top of the cube and kind of see what I mean. So again, we want to parameterize our surface. So we're taking r of blank blank. This is equal to x, y, and z. Do we have a question? Yeah, minor point. But why isn't the unit cube centered at the origin? Why is it just back and forth? You know, when you say unit cube, you want kind of each side to be length 1. And of course you can center, like put the very center of the cube at the origin, but then like you're going to 1/2 in each axis. And it's just a bit more awkward, I guess, to write everything down. It's the same cube, right? It's at least the same volume. It's just translated a little bit. But this is nice because you can use the planes, well, for the top of the cube, you can use the plane z equals 1. For the front or the right side of the cube, when we're looking at it this way, you can use the planes x equals 1 or y equals 1. And for the other 3 sides, you can use x equals 0, y equals 0, or z equals 0. So that's just kind of a nice thing about orienting the cube this way, rather than putting the center in the center of, or the origin in the center of the cube. And then you have plus or minus 1/2 for each of your planes. And I don't know, I think 1s and 0s are just a little bit better. So that's kind of the reason why 1s and 0s are nicer than fractions and negative fractions and all that. Okay, so great. So we kind of already talked about this, but z equals 1 is the top of the cube. And so if we want to use that information in here, well, this is probably our easiest parameterization yet. That's it. We got our 2 variables, and this is a nice vector valued function. And it's nice that, you know, the shadow in the xy plane is a square already. So we could also write down x and y between 0 and 1. Okay, so we have our surface. We need the partial derivatives, our x and our y. Well, again, these are pretty easy. And actually, I want to pause here. I want to scroll back up to, I'll zoom out a little bit. So looking at this surface, tell me it, or I guess I'll just have you guys look at it a little bit and kind of look at these and look at the top of the surface. And look at it and say, okay, well, the parameter, what we're parameterizing is this top of the XY plane, and we have our little cutout square here. And if I wanted the partial derivatives of this parameterization, we did that, but the partial derivatives are really just some kind of slope vectors, right? So really what we did is we said, well, here's our R sub X and here's our R sub Y. It's pointing in the 1, 0, 0 direction and the 0, 1, 0 direction. And so, this example is nice to where we could have seen that, oh, well, those are our two slope directions. And now if we wanted to take the cross product of these, again, if we remember back, like I cross J is what we're doing here. I'm going to skip all of the work, but you guys will find out that you should get a 0, 0, 1 or 0, 0, negative 1 if you switch them around. Again, it doesn't matter since we're taking a magnitude. But altogether, we get a scaling factor of 1, meaning we're in the right coordinates and we don't really have to worry about it too much. We're in the right coordinates and we're using like nice parameterizations of our coordinates. We're not shifting or scaling or anything like that. So great. And so if we wanted to set up an integral, we have 0 to 1, 0 to 1 of x, y, z, which is 1 in this case, times 1 dx dy. And if you go through this all, well, you would get a 1/4. Okay. I do want to make this a little bit of a point, just for a second. I'll zoom out so we can see most of this. For this surface, this entire cube here, what we did was parameterize the top. But if we wanted to parameterize, say, like the right side, well, again, we would need to do some sort of R of blank blank. It turns out the right side, we're using the plane y equals 1. And so you could write this down as an R of xz, which is x comma 1 comma z. And you can go through all of this work again. You can figure out the bounds. Well, for x and z are still going to be 0 to 1. And you could write all of this stuff down, and it turns out you're going to get the exact same integral for this right side as you would the top and as you would the front. But something else that you would need to consider is this function g. So g in this case on the right side, right? This would still be, or this would be x comma z, which is certainly different from x comma y that we had down here. It turns out the bounds are all the same, and so it doesn't quite matter in this case. But if this wasn't a cube, instead if this was like a rectangular prism or something like that, and maybe z was shifted up to height 2, this might come into play. This might matter. So depending on your function, if it's not super symmetrical like this, and you don't have a super like symmetrical surface, you would honestly have to go through and compute all 6 of these surface integrals. And I'll also say, you kind of have to go through that and do it in this example too, because what if you were to look at the bottom of this cube? Well, the bottom of this cube, you're looking at the plane z equals 0. And if you were to go through and plug that into your function g, well, that's going to change your value of the integral a little bit. So something to consider. For surface integrals, depending on what your function is, you might not be able to use symmetry. You might have to actually honestly break it down into 6 different surface integrals and set them all up individually. So that's something to consider. Something else to consider that we won't really focus on too much is orientability. Or really, this should be an orientable surface. So definition: a surface is orientable if there exists, oh, why am I zoomed back out? If there exists a continuous assignment of normal vectors to points on S. So example, if you take a sphere, then at every single point, you can assign a normal vector, right? I'm just going to do it on kind of the outer shell here because we're working in 2D. Right, so at every single point on a sphere, you can assign a normal vector that is either pointing to the outside or the inside. It doesn't matter which one, but you need to be consistent. So in this example, I pointed everything outside. A non-example, and everything that we've ever worked with ever in this class so far is an orientable surface. And everything except this non-example and one other non-example that I will point out are the only 2 times that we will ever see something that is non-orientable. So this is a point that we should pay attention to, but we're not going to care about. That's not where the umlaut goes. It's over the O. The Mobius strip. Right, so the idea is, and I wish we were kind of back in person for this. This is my drawing of a Mobius strip. You take a rubber band, you cut it at one place, and then you twist one of the ends once, and basically you get this Mobius strip. The idea is that if you were to follow your pencil around this thing, well, if you start on kind of the inside here, and you followed it all the way around, once you get to this twist, you are now on the outside. And so if you were to continue to follow back around to this point over here, the original one we started with, you would get back a normal direction that is outside. And this is bad. This is non-orientable. You have a normal direction inside, which is also outside, and that's no good. The other example, which I will not try to draw, is a Klein bottle. So if you haven't seen either of these things before, go ahead, Google them, like check them out, go to the Wikipedia pages. But these are non-orientable surfaces. We are not going to deal with them past today. But orientable will be an assumption that we kind of need to have. So I'll end the lecture there. And on Friday, we will start talking about surface integrals dealing with vector fields. So see you guys then. Don't forget about the problem 1 on the homework 10. Write vectors.